We're looking at U substitution in this video. Now, I'm really excited about U substitution because it can help us tackle a whole bunch of integrals that we couldn't before. It's sort of like the reverse of the chain rule in a sense. Basically, what you're doing is you're looking for something called U, and then you're hoping to find du dx in the integral. So for this integral, I'm going to set U equal to x squared plus 1. And you can probably see that U is sitting right up there. Then we can work out du dx, and it happens to be 2x if we differentiate this thing down. And guess what? You can probably see that du dx is sitting here. So the whole integral essentially just becomes the integral of that bit is du dx times e to the power of u. Now, really important at this step, you should not have any x's in your integrals, apart from like the x on the dx bit. Speaking of, that x is about to go away with this wonderful magic trick called U substitution. Okay, so we've got du dx there. I'm just swapping the order of this to make it more obvious. Now, mathematicians hate when you do this, but basically the dx's sort of cancel. They are not fractions, but they sort of behave like fractions in this one particular case. They sort of cancel off. So we're left with e to the u du, and I think we know how to integrate e to the u. It's e to the u plus some constant c. So that's great. We've integrated the thing. Now, you might be wondering, well, what's this u thing? So if somebody asks you to integrate that horrible thing with all the x's and you just say it's e to the u, they'll probably look at you funny. That is definitely not the integral as they had asked for it. We need to sub back in what u is. So u is x squared plus 1, so it's e to the power of x squared plus 1 plus c. And that's the integral. I just want to take a sec to differentiate this. So if f of x is e to the x squared plus 1, f dash of x is going to be e to the x squared plus 1 times the baby, which is 2x. And that is indeed what we started with. So we know that it's the correct integral. Okay, next we've got what is essentially the same integral. Last time this was 2x, now it is just 2. We're not going to do this one because I want to point out that it is impossible. Integrals are very, very weird. If we try to do U substitution on this, we can do the same thing. U is x squared plus 1, and du dx is 2x, like what we had before. But we don't have 2x in the integral, so we actually can't do this one. It turns out that it is impossible in terms of functions that we sort of know in specialist maths. You can define the solution to be something called the error function, which mathematicians do. But it's sort of like a cheat way out because you can't really do the integral. They've just defined the answer to be a new function, which they call the error function. So yeah, not really possible to do. Okay. Integral of tan. So what we need to do is use a trig identity on here. So sine over cos. And then we need to pick our u and v very carefully. Not u and v, sorry, u very carefully. U is usually the thing that is trapped in some sense. That's my best way of describing it. So see how the cos is trapped underneath a fraction. U will be cos. If we set u to sine, it just won't work. And here, see how x squared plus 1 was trapped up in the top of an e. So that's why we set that to be u. You'll get a hang of figuring out what u should be. But essentially, it's always the thing that's trapped. Du dx will be minus sine of x. Cos goes to minus sine when you differentiate. So this whole fraction becomes, it's u on the bottom, and on the top it's sine of x, so that's minus du dx. Just like that. And then we've got dx at the end. Same thing's going to happen. The dx's will essentially cancel off. So it's minus du over u. Or if you want a nicer way of writing this, it's minus 1 over u du, just like that. Okay, if we do this, the integral of 1 over u is log. And we still got the minus sign, and we got to put a plus c. And then we just have to sub it back in what u was. So it's minus log of the absolute value of cos of x plus c. C is a real number. I really encourage you to try and differentiate this and see if it does give you back tan. Hopefully it will. Okay, next we've got definite integrals. Now, there's sort of two ways to approach these. So one way you can do it is sort of the standard way that you might expect. So do U substitution and then pretty much like put x back in and then sub in the x values. So that's what I'll do first here. So the integral of. Now, U is the thing that is trapped. This area is nice and free. It's just being multiplied. That's all good. This thing here is trapped because it's sort of like trapped in being raised to a power of 5. So U is the thing that's x cubed plus x squared. And you'll know that you got it right or wrong pretty quickly, because if I work out du dx, it should be the other thing. So 3x squared plus 2x. Oh my goodness, it's not. The other thing is 9x squared plus 6x. What could we do? Well, this thing here is just 3 lots of du dx. Everything's times by 3. So that's fine. So the whole integral just becomes 3 lots of du dx times u to the power of 5 dx. The dx's will cancel. So what you're left with is 3u to the 5 du, just like that. And we can just integrate that. So it is 3u to the 6 over 6 plus c. C is in R. No. All right. If you want, this is u to the 6 over 2 plus c. Now, I actually don't need the plus c here because this is a definite integral. So I was going from 0 to 1. So this whole thing will just go from 0 to 1, just like that. Okay. Now, really important, this is x equals 1 and x equals 0. Got to be really careful about that. So we have to sub back in what x was. So what u was. U is x cubed plus x squared. So we get x cubed plus x squared to the power of 6 all over 2. We've got to integrate that from 0 to 1. And now we can work with this. I'll show you a little trick. You can actually pull the half out the front of the integral. And then we got x cubed plus x squared to the power of 6 from 0 to 1. And then we'd have to deal with the pesky half hanging around the whole time we're doing this. Okay, first one is 1 cubed and 1 squared to the power of 6. And then it's 0 cubed and 0 squared to the power of 6. And if we work through this, you're going to get a half of, let's see, 1 plus 1. So that's 2. And we're raising that to the power of 6. And then it's just take away 0. So this is, well, it's 64 over 2, but it's 32 as the answer there. Okay, so that's one way to do it. The other way that you can do it is with keeping u as just u. So I'll show you that alternate method. This method is quicker. So if you want to use this second method, it will make your life easier. But the issue is it's a little bit more confusing. So you take that trade-off if you want it. So 9x squared plus 6x, x cubed plus x squared to the power of 5 dx. Beautiful. All right. So we're going to do the exact same thing. So we're going to use the same u substitution. So what was it? It was 3 lots of du dx here. And it was times u to the 5. Now, really importantly, these bounds were x is 1 and x is 0. I'm going to change this to u bounds now. So if we look at u here, when x is 1, u is 1 cubed plus 1 squared, which is 2. And when x is 0, u is 0 cubed plus 0 squared, which is 0. So instead of integrating from 0 to 1, I'm going to integrate from 0 still 0, but I'm going to integrate up to 2. And now I can do this all in terms of u. We can forget that x even exists. So u is 0 to u is 2. This is 3u to the 5 du. So this is 3u to the 6 over 6 from 0 to 2. So this is u to the 6 over 2 from 0 to 2. So we can do that same strategy as before. We can just go half there. So this is a half. Lots of 2 to the 6 take 0 to the 6. which is going to be 2 to the 6 over 2, which is 32. So you see we get the same answer. The U method looks longer, but that's only because I was excited to do it. You can condense both to about the same amount of working. So right method, easier, but a bit more confusing. Left method, less confusing, but a little bit longer to do algebraically. And that's U substitution.